Hello, and thank you for watching my video. This is part 5 of the number theory from the multiplication table series, and it is the answer to part 4, which was a challenge video. Now I know that it's only been a short, 4 or 5 months or something like that, and everybody probably really needs more time. But unfortunately, I am compelled by my fan base because the video was absolutely flooded by a comment practically begging for the answer. And here it is. Alright, to recap, we started with the first 20 values of sigma, the sum of divisors of n. And from that sequence mentally with this timer, I wrote down a sequence of numbers underneath, which were a mystery function. And then I proposed that this mystery function was indeed the sum from k equals 1 to n of n mod k. And the point of the challenge was, how did I do that from the sigma n values in my head? Or more to the point, how could anyone do this? I mean, it doesn't seem like the kind of sum that there should be a quick and simple closed form answer for, if it is indeed a closed form. What? In part 1 of this series on number theory from the multiplication table, we looked at the area made up by the columns, and it's obvious that the height of each of these columns, which are unit width, are going to be n divided by x, floor function. There's no fractional parts. And doing that, we get all the numbers that are equal to n or less that are to be had on the multiplication table. So we can add it up this way and we get 14. Similarly, we can account for the area using the tau function, because if there are two numbers that when multiplied together give us n, then the tau function, the number of divisors, is going to give us all such possibilities. Duplicated over this line of symmetry, this diagonal axis of symmetry which goes through all the squares. So 1, 2, 3, 6 are the divisors of 6. And so we can account for this area the same way, just by counting and adding up the tau function of all numbers less than or equal to n. So for 6 we get 4. For 5 is a prime, we're only going to have 2. Same for 3, we're only going to have 2. When we have a square, we are always going to have an odd number because we get this extra one in the middle. And of course 2 is prime, so another 2 and then 1. And so we're accounting for the same area, and therefore these two ways of counting the area are going to be equivalent. Then in part 2 we looked at the thing up to 7 rather than 6, and we note that in the integer area section, the lower curve, obviously it's prime, so there's only 2 divisors where we're going to get a 0 for 1 to 7. So we're only adding 2 to what we had before, which was 14, so now we have 16. And because it's prime, we can never have a 0 in the middle. And we basically convert this to 7 mod x over x as an expression of the fractional part, and it's the same equation that we had before. But the thing now that we want to look at is that the numerators here are sequence 7 mod x for x equals 2 to n minus 1. That's sequence 1, 1, 3, 2, 1. Okay, so we want to make this observation. how many times of all the numbers from x equals 1 up to n is 1 used as a divisor? Well, obviously 7 times, because it's there for every x. 1 is divisor of every x. So we can get ourselves a sum from x equals 1 to n of sigma x, where sigma is the sum of divisors. Tau was counting the number of divisors. Sigma is the actual sum of the divisors themselves. So out of 7 numbers, 1 appears 7 times. So we can add up this sum a different way. And we can say 7 times 1. And then how many times does 2 appear as a divisor? It doesn't appear in any of the odd numbers, but just the even numbers, which are 2, 4, and 6. So we have 3 times 2. And similarly, we have 2 times 3.
1 times 4, 1 times 5, 1 times 6, and 1 times 7.
So recall from before, 7 plus 3 is 10, is 12, 13, 14, 15, 16. So we have the sum of tau is equal to 16. By forming this convolution, and we're going to get these numbers: 7, 6, 6, 4, 5, 6, and 7, which is 7 plus 6, 13.
Plus 5 is 18, plus 4 is 22, plus 6 is 28, plus 6 is 34, plus 7
is 41. And that is the value of our convolution, the sum of these product pairs. So is that the sum of sigma x for x equals 1 to 7? It must be. It has to be, right? We have x
equals 1, 2, 3, 4, 5, 6, 7.
Sigma x equals
1, 3, and then 4, 7, 6, 12, and 8. And that's 1, 4, 8, 15, 21, 33,
41. All right, yeah, so that's what we're talking about. Now let's do one more observation here, a couple more observations here. We have
the sum from x equals 1 to 7 of sigma x equals 41.
Well, now let's take
7, 6, 6, 4, 5, 6, and 7.
The value at the top of every column. So we have 7 columns, 7 numbers, and let's add those up.
7, 13, 19, 23, 28, 34,
41. Yes, the tops of the columns, the values, will always sum to our convolution. So of course these are going to sum to the running sum of sigma x. Let's consider a mythical number that does not exist, and that would be one that is ultra smooth. Basically, n divided by x is an integer for all x. It can't exist. If there were such a mythical example, then we would have, and let's say we'll use 7 as our example, say this was it, then we would have 7 at the top of every column. And thus the sum of the tops of every column would be 7 times 7, or 7 squared. So it's mythical, it doesn't exist, it's impossible. However, it is a benchmark. and we can ask what's missing. Well, here what's missing is 0.
Here, what's missing is 1. Here, what's missing is 1. Here, what's missing is 3. Here, what's missing is 2. And here, what's missing is 1.
So 7,
7, 7, 7, 7, and 7.
So these are the numbers that we would need to add to the numbers less than 7 to mock up our mythical number that's divisible by every number below it. What are these numbers? Well, they are just the residues. So the fractional part, as we recall, is going to be 7 mod x over x. So the numerators, the 7 mod x, are these numbers. 7 mod x, just not divided by x, not the numerator. So this is the these numbers here, 1, 1, 3, 2, 1, are the sum from x equals 1. We'll go ahead and say, do the full range, because it's going to be 0 here and 0 here, obviously. But it's basically the sum from x equals 1 to n of 7 mod x. And so we have our little theorem here that the sum, I'm going to switch to k equals 1 to n of sigma k plus n mod k equals n squared. And to do the challenge of the part 4, you just keep track of the running sum, and you think to yourself where you are. 1, so 1 squared minus 1 is 0. 2 squared is 4, minus the sum is 4 is 0. 4 plus 4 is 8. 3 squared is 9, minus 8 is 1. And 8 plus 7 is 15. 4 squared minus 15 is 1. 21. 5 squared minus 21 is 4. Dot, 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 dot. So if you can keep track of the squares where you're at and this running sum, then you can do it. And with this in hand, we can find some corollaries in number theory. Let's define this sum function R of n as the sum from k equals 1 to n of n mod k, our residue sum, Rn. And then we get our sum of sigma k for k equals 1 to n is equal to n squared minus Rn. So now let's let n be a perfect number, then sigma n equals 2n, so we can take that out of the sum on the left hand side and then have our n squared. This should be minus Rn, and we'll be fixing that in a jiff. And then this sum up to n minus 1, well, we can replace that with n minus 1, the quantity n minus 1 squared minus r of n minus 1. So let's do that. Let's break this out, and we're going to put that on the left, and then we're going to bring the 2n over to the right and work this out in terms of Rn and see what is between r of n and r of n minus 1, so to speak. So I'm going to fix this mistake of the plus sign there, because I make it again here in red. And so let me refresh the screen. Okay, and so the way it works out is the n squared minus 2n cancels out on both sides, and then we can rearrange it and have this expression: r of n minus r of n minus 1 equals -1 when n is a perfect number. In fact, if and only if n is a perfect number, is this the case. And we can look at the general case between n and n minus 1 to see what the difference of residues is, like over a span, because we could use n minus a. But look at the n minus 1 case. We're going to write out the theorem for n squared for n, and then for n minus 1. And then we can subtract the latter from the former, and we are going to get 2n minus 1 minus r of n, the quantity r of n minus r of n minus 1, equals, oh, I made a mistake there, I didn't have a closing parenthesis, equals sigma n. So we get this expression for sigma n in terms of rn and r of n minus 1. All right, I've written it or copied it up here. It's still missing that right bracket at the end of the first left-hand side of the equation, which is annoying. But anyway, the r n minus 1 is positive. So anyway, but because we can express sigma n this way, then we can plunk it into Robin's criteria for the Riemann hypothesis, so we can restate we can state that the truth of the Riemann hypothesis is equivalent to the assertion that the sum of the residues of n minus 1 minus the sum of the residues of n is less than the quantity e to the gamma times n times log of n minus 2n plus 1 for n greater than 5040. Since it's just a restatement of sigma, of the sigma function in terms of in terms of the residue sum function, we can also just substitute it into the Largarias criteria for the Riemann hypothesis, and then get this r of n minus 1 minus r of n is less than the harmonic number plus e to the power of the harmonic number, of the nth harmonic number, times the log of the nth harmonic number, and then all that minus 2n plus 1. So I think it's interesting because the residues here are closer to home to the harmonic number, as we've already seen. All right, well, because the residue difference here is just an alternate expression of the sigma function itself, this is ultimately going to be a circular argument, if anything. But it is interesting that because it gives us some intuition for what's going on. So here, let's look at the residues for 11 and the residues for 10, and then subtract them. And obviously, we have, other than at 1 and n, where we're going to have 0, we get negative 1s across the board because 11 is prime. And if we do the same thing with 12 and 11, because 12 is smooth and has many factors in between, everywhere that a factor appears for 12, we're going to get a 0 in the middle. And so when we subtract, we're going to have a positive number, which will be equal to that divisor minus 1, and then negative 1 everywhere else. And that's it. That's the complete constitution of these differences of residues. So the difference of residues in this expression is always going to be negative of the quantity n minus 2 plus the aliquot divisors. Aliquot divisors meaning all the ones in the middle, all the divisors except for 1 and n itself. So the sum of aliquot divisors when n is a prime is 0, because there are no divisors between. In other words, in the general case, if k is a divisor of n, then we're going to put a d up there. If it's a non-divisor, we'll put this n prime. And so the difference is always going to be -1 for the non-divisors and d minus 1 for the divisors. And so when we take the difference, then we're going to get, because that -1 is actually there in every aliquot entry between 1 and n minus, and between 1 and n, then we just need to add the aliquot divisors of n to basically to equate this sum. R of n minus 1 minus r of n is equal to negative the quantity n minus 2 plus the aliquot divisor sum. So we can add n plus 1 to the aliquot sum to recover sigma n proper, and we get sigma n minus 2n plus 1, and if we substitute that back, then we recover the original Largarias criteria. So indeed, it is a circular argument, but we can know some things, which, for example, when it's prime, it's then r of n minus 1 minus r of n has to be a negative number. And where else is it negative? Well, obviously for near primes, in fact all near primes all near primes would have to be negative. And then here's some examples. Here's a triple. 110 is -3, which, when you think about it, it's 2 residue units away from being a perfect number. And so you can divide a by n. Now this doesn't tell us very much, but it other than that we can use the residues, difference of residues, as a measure of smoothness to a certain extent. Smooth numbers going to be positive and large for very smooth, or more smooth. The more smooth it is, the larger it is. So how can we, is there a way to formalize this and in terms of smoothness? And the answer is yes. Now I have an interesting combinatorial method of showing the following, but I'm just going to refer to what is well known from analytic number theory, and that is Apostol's theorem, which gives us the average order of the sum of sigma k for k equals 1 to n. That's the same thing that we have here, expressed as n less than or equal to x, sum of sigma n, is equal to zeta 2 times n squared over 2. So we got our x's and n's mixed up with this right here. So let me just show you what that's saying in terms of what we're doing here. It is saying that the sum from k equals 1 to n of sigma k is on average order of zeta to n squared over 2. So we can take our expression for sigma n equals n squared minus r of n minus the sum from k equals 1 to n minus 1 of sigma k. And so that is going to be on average order zeta 2 times n minus 1 squared over 2. We can do something similar here, that sigma n is going to be zeta 2 n squared over 2 minus zeta 2 of n minus 1 squared. We're talking all here average order. And then let's bring this over to this side, so we get minus this, which is, I mean, it's minus here. So we bring it over to this side, we're going to be adding it, and we can see that that just cancels with that. And let's bring our minus n squared over, and then we get equal to r, negative r n, or to clean this up, r of n, the average order of it, is n squared minus zeta 2 n squared over 2. Okay, so let's divide each side by n squared, and we're going to have Rn over n squared, expected average order about, well, let's express it as 2 minus zeta 2 over 2. And this, very similar to sigma n over n, is going to be a measure of smoothness. So we can do exactly what folks do with this figure here, and look for deviations, look for maximums over the expected value. And if any n establishes a new maximum, then we're going to say, let's call it residue-smooth, because it's a different kind of smooth number. There's only about a couple dozen already. So many ways of doing smooth, defining smoothness. And this one here is kind of a natural, very natural way of defining smoothness. So let's look at the numbers we get that are residue-smooth. Okay, well, let's just start with our measure, and as we did here above, looking at ones that are not smooth, which ones give a negative measure, which ones are less than the expected value. So you see we've got our 2 minus zeta 2 over 2 minus the sum of the residues for n divided by n squared. So that's this variable a, and if a is less than 0, we're going to print n, and then n mod 6 just for other purposes, and then a itself, which is this which is this measure, and then I also included n times a, and I forget exactly why. But anyway, point being is that now we can see that we are very much restricted to odd numbers, and it's going to be very tough, if not impossible, for an even number to, in fact impossible, for an even number to have a negative measure of r of n over n squared. So let's move on to the actual, maximum, or smoothness in terms of achieving looking at maximally smooth numbers by this measure. All right, here I went up to 2000, I believe, here. But I wanted to show you this. This is the measure, and this is for all n, going up to, I think, like 20,000, but we only have a 100 number span here, and this frame gizmo advances that. So we can see it looks very much like the other measures of smoothness and stuff like that. And for example, let's go to 50-40, where the Robbins criteria, which is a very smooth number, and we see the big spike up here and the negative before it, 50-39. It's not necessarily it's going to be that there's going to be a big negative spike prior to a smooth number, but it certainly is going to happen more often than not. Like if we go to even now 1080, which is double of 50-40. Let's see if we can get there. I seem to be frozen. Maybe I don't have enough numbers in here. Anyway, it goes like that. All right, move on now. All right, so here it is. Here's we're going to keep track of maximums and look at smoothness. And 1, 2, 4, 6, 12. So they're pretty much hitting all the popular smooth numbers in the lower areas there. And I did this all the way up to 1.5 million and got the last one here, 942,480, which was a new maximum for our measure of r n over n squared. So how does this compare to other smooth numbers? Having some troubles here. All right, even abundant numbers, and these refer to the online Encyclopedia of integer sequences designation. There is no sequence in OEIS yet for what I'm calling the residue-smooth numbers, or residue-abundant, or super abundant residue. I don't. Maybe in comments section you can give me your thoughts on how these things should be called. So the ones in these are all the even abundant numbers, and the ones that are pink and bold are the ones that are also residue-smooth or residue-abundant, whatever we want to call them. Okay. The crowded numbers, sequence A066523, and we can see that 50, 40, and 10 and double it are in our list, and these are the ones that are in common with the crowded numbers. Similar thing, miserable average divisor numbers, and it looks like the correspondence ends kind of low, but these things don't really go up to too many places, or too many numbers in the sequence. Then somebody defined deeply composite numbers. And a lot of these are sort of artificial constructions. Well, I shouldn't say that, but the distinctions, I'm not sure. Some distinctions are more important than others, I suppose. Highly composite numbers. We are, also have the numbers that match those. The superior highly composite numbers, OEIS A002201, also petering out in terms of correspondence after 50-40, which doesn't really mean anything. It's not a conclusion, just an observation up to these low numbers. Highly abundant numbers, super abundant numbers, colossally abundant numbers, and so many of their lower ranks. I'm not sure what that means. I guess that's just the numbers that are corresponding Yeah, so that's the case. At some point in time, when I was playing with this originally, I, for some reason, was thinking about calling them the elite abundant numbers. The reasons escape me now. But anyway, that's what you see there. Those are the residue-smooth numbers, or whatever we're going to call them. And the ones in pink are the ones that correspond to other known smooth and abundant numbers as just listed above. So 4032 is the first outlier. There may be other versions of smooth numbers that include it, but I don't see it anywhere else. So anyway, that's what we got going on. At some point I've got to submit a new OEIS sequence on these. We can see they do thin out just as quickly as colossally abundant or super abundant, things like that. And that's as far as I've computed up to there. So this is interesting, and maybe we've got to do some more videoing on these numbers. But yeah, in the comments, after you smash the like button and subscribe, leave a comment and tell me what we should call these numbers. There are some more interesting insights available from researching along these lines here, especially over spans of the sum of sigma, like from n to n minus a, and see how those have a little bit of a structure to them. But that'll have to wait for a future video. I'm going to wrap this one up. Thank you very much for watching. God bless you. And please click on the PayPal link in the description and contribute to support my research.